Hi, welcome to my channel Rocío Chávez Ciencia de Datos. Before starting with today's video, I want to let you know that I am preparing material to explain in detail how principal component analysis works. One of the core parts of this technique involves creating new variables that are independent, meaning that the information they contain is not redundant. This is where the topic of matrix factorization into eigenvalues and eigenvectors, also known as eigen-decomposition, comes in, which is what we will see today. On this occasion, I will focus on the mathematical part, and later I will make a video explaining these concepts in a graphical way. This mathematical technique can only be applied to square matrices. It involves finding a set of scalars and vectors so that the original matrix can be represented as a linear combination of these. This transformation helps us understand the characteristics of a system, allowing us, among other things, to analyze it with less data than we originally had, reducing the necessary resources and processing time. It is widely used in various areas, such as physics, data science, and artificial intelligence. I will present an example of how this equation works. Once we know the eigenvalues and eigenvectors, we will multiply the original matrix by the first eigenvector, which is the first column of the eigenvector matrix. On the other side of the equation, we will do the same with the first eigenvalue and the first eigenvector. And we will see that it yields the same result. If we multiply the first row of the original matrix by the eigenvector, we have 1 times 2 plus 4 times 1, which gives us 6. We multiply the second row and we get the 0 that appears here. We multiply the third row, 3 times 2 plus 1 times 0 plus minus 3 times 1, and it gives us a total of 3. If we multiply the eigenvalue of 3 by the eigenvector, we see that it yields the same result, 603. We do the same with the other eigenvalues and eigenvectors, and we see that the formula is satisfied for all three. What if we wanted to find the original matrix using only the eigenvalues and eigenvectors? If we rearrange the eigen-decomposition formula, we can obtain the original matrix by multiplying the matrix containing the eigenvectors by the matrix of eigenvalues and the inverse matrix of eigenvectors. Now that we have seen an example of how eigenvalues and eigenvectors are multiplied, let's see how they are calculated, starting with the eigenvalues. And once we have obtained the eigenvalues, we will calculate the eigenvectors. We start with the original equation. Move the lambda times eigenvectors to the left side of the equation. Factorize them and set the difference between the original matrix and lambda times the identity matrix equal to 0. To make the explanation clearer, I will use this small matrix, which is also symmetric. Although it is not a requirement for it to be symmetric, it only needs to be square. I will take advantage of this characteristic to show you how, when you have a symmetric matrix, such as the one used in principal component analysis, the eigenvectors obtained are orthogonal, which is one of the things that is sought in PCA, that the new variables do not contain redundant information. We said that the original matrix minus lambda multiplied by the identity matrix was equal to 0. After performing the subtraction, we are left with this matrix, which is 3 minus lambda, 2 minus 0, 2 minus 0, and 3 minus lambda. To obtain the value of lambda, we will obtain the determinant of the matrix. We do this by multiplying the elements of the main diagonal and subtracting the multiplication of the other two elements. And we obtain the characteristic polynomial of the matrix, which in this case is lambda squared minus 6 lambda plus 5 equal to 0. To obtain the values of lambda, we solve the quadratic equation and see that the roots of the polynomial are 1 and 5. Before calculating the eigenvector, let's see how the sum of the values contained in the eigenvectors is equal to the trace of the matrix, that is, the sum of the values of the main diagonal of the matrix. Now let's calculate the eigenvectors. We will start using the eigenvalue equal to 1. We multiply both sides by the eigenvector, whose value we still do not know. From here, we obtain two simultaneous equations, which are 3 times b1 plus 2 times b2 equals 1 times b1, and 2 times b1 plus 3 times b2 equals 1 times b2. By solving these simultaneous equations, we obtain that v1 is equal to minus v2. We substitute the values of v1 and v2 into the original equation and see that indeed the left side of this equation is equal to the right side. Another piece of information we can obtain from the eigenvector is its magnitude, which in this case is equal to 1.4142, which is the square root of 2. Why am I telling you this? Because in most cases, the programs used to obtain the eigenvalues and eigenvectors of a matrix deliver eigenvectors whose magnitude is equal to 1. However, as we can see here, that eigenvector also satisfies the equation's equality. This means that there is not only one eigenvector for each of the lambda values. In this slide, I show you how to calculate the magnitude of a vector, just as a reminder of how it is done. The magnitude of a vector is equal to the square root of the sum of its components squared. In this case, it is equal to the square root of 4 squared plus 3 squared, which gives us a result of 5. You may wonder how programs calculate and deliver us unitary eigenvectors. Here's how it is done. First, we square both sides of the equation to remove the square root. Then, we divide everything by 2 and arrange the terms so that they are squared without altering the result. For example, in this case, we apply the square root of 2, which was not squared. If we divide minus 1 by the square root of 2, we get minus 0.7071. And if we divide 1 by the square of 2, we get the second element of the eigenvector. Now we have an eigenvector whose magnitude is equal to 1. We will now calculate the eigenvector corresponding to lambda equal to 5. Finally, we will see how we can calculate the distance between eigenvector, that is, the angle between each of them. We can obtain this information with the dot product, also known as the inner product or scalar product. Knowing the angle between two vectors helps us realize whether there is correlation between them, that is, whether they contain redundant information. For example, in the first graph, we see that the dot product is equal to 1, which means that the angle between the vectors is equal to 0 and that both vectors point in the same direction. It is, they are correlated. In the second graph, we have two vectors forming a 90-degree angle, which means they are linearly independent. While in the third graph, we see two vectors whose dot product is negative. To obtain the dot product of two vectors, we simply multiply the corresponding elements of each vector and then add everything up. Let's calculate the dot product of the eigenvectors 1 and 2 that we just found. And we see that it is equal to 0, which means they do not contain redundant information. To obtain the angle formed by the vectors, we substitute the values in the dot product equation, solve for the cosine function, and apply its inverse function. As I mentioned at the beginning of the example, when you have a symmetric matrix, its eigenvectors are orthogonal, that is, they are perpendicular.